Okay, so a number of you wanted me to go over the examples from exam two, so I'm going to just kind of walk through them, and I'm going to do this in a very uh, basic and patient way. So for some of you, this will feel quite a bit slow, but I want to make sure that I'm kind of going through all the steps. So one of the examples that gave some people a challenge was this one. So and the actual numbers you might have gotten would have been different because it randomizes them. But we've got an insulated house with 10 windows and 2 doors. And it has this flat ceiling, so we're making ourselves a very simple box, right? For the purposes of the exercise, there's no heat loss to the ground. That makes our calculations really easy. And we want to simply calculate what is the effective R value of the entire above grade enclosure. So we're given some components. We've got walls, which exclude windows and doors, but are the total R value of the wall. So if you were thinking about a framing factor or something like that, you don't have to, because we don't know what the wall is made of. We just know that its total R value is 7.4. Not a great wall. Probably a good hint that this is a masonry wall. And then we have windows and doors. Those are separate. And we've decided to make them really excellent windows because, again, it randomized numbers to something that's a pretty good window. And we have that R value, and then we have the R value of the roof. So the first thing we need to do is take that table, and we're going to have to do an area weighted UA calculation, right? And this should feel really familiar, right? To calculate the UA, we're going to take the U factor of element 1 and times it by the area of element 1 plus the U factor for area element 2 times the area for element 2 and so on. And we also are going to want to remember that 1 over R is the U factor. And so we can rewrite the UA formula like this, where you do 1 over R for area 1 times area 1 and so on. And we also know that the total area is going to equal the sum of all the component areas. And so if we want to convert that total UA to a U factor for the entire, for the weighted U factor for the entire thing, that's what we're going to need to do. So, right, so that's going to be our ability to get the U factor. And then, of course, 1 over U is going to be the R. That is what we're looking for the answer. So we can set up this particular example with 1 over the R value of the wall times the area of the wall plus 1 over the R value of the window times the area of the window plus 1 over the R value for the roof times the area for the roof. And to make it a little easy, I've put all the U factors or R values, right, since one is the reciprocal of the other, in green, and I've put the areas in red just to help us kind of visually track what we're doing. So 1 over, you can read these numbers, right? So basically we've plugged in the numbers into our formula, and now we've converted those R values into U factors, right? So we can see what those are. And then if we simply add each of those things that we calculated inside the parentheses, right, then we have the UA, which, we just add that all up. That's our total UA. And we want to find out what is the UA. Once we've divided it by the area, we can find the U factors. So the area of the walls and the windows and the roof together is the total. So we can add that together. And now we have the total. And now we know that if we have the UA, the U is going to be the UA divided by the A, by the area, right? And we can take that and run it through, and we see that our U factor is 0.099, and we take the reciprocal of that, and we can see that the R value is going to be 10.12. So obviously your specific numbers would have been different, but this would be the process that you would go through to calculate it. Now another question was one about a kind of a simplified house. Again, the numbers you used would be a little bit different. So we have a total shell R value of 18. In other words, that calculation that we just did on the prior example has already been done for you for the total shell R value, right? Because it's all of that stuff has already been done. And we have the shell area that's also been calculated for you, or it's been provided. We have the floor area, and we also have the volume. So then we also have the average air changes per hour. This is a relatively tight building. Okay, so and we have our number of heating degree days, and we want to calculate, assuming no heat loss to the ground, what is the total, that means conductive and convective, annual normalized heat loss, and we want that in kBTU per square foot because that's your measurement of EUI that everybody's comfortable with. So we're going to have to use a conductive equation and an air leakage equation. So our conductive heat loss should be familiar, but I'm going to step through this just to remind you how the units cancel, right? So the square feet cancel, the degrees Fahrenheit cancel of heating degree days, which is degrees Fahrenheit days, right? And then the days, in order to get this for a seasonal or annual use, we need to convert our days to hours. They're 24 hours per day. And now we have the U factor in BTUs per hour, but because we want energy and not power, we now have that the hours cancel, and now we have our answer in BTUs. For air leakage, we have a very, very similar process. We start out with the volumetric heating capacity of air, that's the 0.018, times the volume, times the air changes per hour, times the difference in temperature, or the delta T, times time, right? Because we want it in energy, not power. So we want to replace delta T times time with heating degree days, because that's basically what heating degree days are. But air changes per hours is in hours, and heating degree days is in days, so we have the same need to use the 24 hours. So again, we're going to cancel the units that naturally cancel, including the hours that cancel and the days that cancel for heating degree days. And now we have our simplified equation is going to be the seasonal air leakage heat loss is going to be 0.018 times the air changes per hour times the heating degree days times 24 hours. So now we can run this equation. So I've put off on the side this R value, the given information, the shell area, the floor area, the volume, air changes per hour, and heating degree days. So first, let's look at the conductive heat losses. That's the UA times heating degree days times 24 hours. So remember that U is 1 over R, so we can calculate 1 over 18 is 0.055. So that's our U factor. And we can plug that into the other givens, right? We already have the area is 4,000 square feet. We already have the number of heating degree days and 24 hours. So that 29 and almost 30 million BTUs is our annual conductive heat loss. Now we have to do the air leakage heat loss, and we take the equation that we had on the previous page, and we're going to plug in our numbers here. So we have 0.018 times 0.22 air changes per hour. And then we're going to use the volume of the house, which is also given, and the heating degree days and the 24 hours. And then we have our heat loss in BTUs. And then we just want to take those two things, the heat loss by air and the heat loss by conduction, and add them together. And we get, with 39 million and change BTUs, we want to convert that to kBTUs, right? So we divide it by 1,000. Now it's 39,000 and some kBTUs. And we divide that by the square feet, which we were given as 2,000 square feet. So this building must have some pretty high vaulted ceilings, I guess. And so their heat loss is 19.8 kBTU per square feet. So that's how we would calculate that one. So here's another question, right? The total R value of a building shell is 20. Again, that's already given. The same thing is calculated given the surface area of the building shell is 3,000 square feet. So that's also already given. This would have been like the first example where we had to calculate it. The inside temperature is 70 degrees and the outside design temperature is 5 degrees Fahrenheit. So we're going to assume no other heat losses. So we're really just using conductive heat losses for this example. And if you're sizing a heating system, what would be the power of the heating system? So that means that this heating system, whatever it is, would need to provide sufficient heat to maintain a 70-degree temperature when the outside temperature is 5 degrees Fahrenheit. So we can plug this into our heat loss, our conductive heat loss equation for power, which is just U times A times delta T. So we take the U as 1 over the R value, right? So 1 over 20 times the surface area, which we've already calculated it at 3,000 square feet. And then the delta T is the difference between inside and outside temperatures. And so the answer is 9,750 BTU hours. That is the heat loss that a heating system would have to make up. This was probably the question that people had the most challenge with, and so we're going to step through this kind of carefully. So in this case, you're charged with specifying a cooling system for the house. The solar and internal gains have already been calculated, but you need to increase its capacity to account for ventilation. So that means that we're not talking about what the total cooling system needs to do. We're talking about how much additional capacity do we need to make sure that the cooling system has above what was already calculated, because we're going to add a ventilation system. And so the ventilation system is going to exhaust 400 cubic feet per minute of stale air and replace it with 400 cubic feet per minute of fresh air. And in this particular example, we don't care how it's done, but we know that there's no recovery on that heat, right? Because we didn't say there was. So this is just replacement of fresh air. So on a design day, right, because when you're specifying a cooling system, you use that design temperature or the design conditions. On a design day, the outdoor air is 92 degrees Fahrenheit dry bulb temperature and 78 degrees Fahrenheit wet bulb temperature. The indoor air is expected to resolve to standard air, right? And standard air is that 75 degrees Fahrenheit at 50% relative humidity. So the question is, what is the additional amount of cooling capacity required to account for the ventilation? And we're going to supply our answers in BTUs per hour, so it's going to be large. So again, I'm going to step through this. When we look at our latent cooling load, right, this is instantaneous power. This is in BTUs per hour, so we want to arrange the equation. Psi here, right, that thing kind of looks like a W, is the difference in absolute humidity, or another word for that is the difference in humidity ratio. So that's in pounds of water for every pound of dry air. So for every pound of air, we need to use the enthalpy of standard air, right? Because we're going to standard air. And we're going to have the pounds of water. That is the pounds of water that are condensed out when we do the removal of excess water, when air conditioning does what it does, right? So, and then cubic feet per minute, we want to change that from minutes to hours. So we have to multiply by 60, and now we've got it in hours. And then, I failed to cross off the second square feet, but our cubic feet, but obviously we want it in cubic feet. Also cancels here, so we can see that we have our simple equation is latent heat gain from that volume of air per minute. And so we can simplify that equation, right? So we've got a bunch of constants here, so we can consolidate those constants. So the equation we're going to be working with is going to be the difference in absolute humidity times the flow rate of the air times this consolidated constant 4842. And that's what we're going to be using. And so we need to add together the latent heat, that is the moisture containing heat in the air, and we're going to add that to the sensible heat to account for both kinds of heat, the total enthalpy that is in the air that we're moving in. So we're going to use these two equations, the latent heat equation with the difference in absolute humidity, and the sensible heat equation, which should look really familiar. It's 1.08, which is these consolidated constants that include the volumetric heat capacity of air times the 60 minutes per hour times cubic feet per minute times difference in temperature. All right, so to do the latent side, we need to find what is the absolute humidity inside and outside. And to do that, we go to the psychrometric chart. And so I've put our conditions that we're looking at up in the top right-hand corner. So we can first look at our outside temperature. So our outside temperature is 92 degrees Fahrenheit dry bulb temperature. That's what I mean when I write dBT. And now we're looking for the wet bulb temperature. And so the wet bulb temperature of 78 degrees Fahrenheit wet bulb is going to be on this wet bulb line. And you can see over here we're at 75, 76, 77, 78 degrees Fahrenheit wet bulb temperature. So the absolute humidity is going to be what we find on the far right vertical axis, right? And so that we can then read off of that what is the absolute humidity of that state point. And here we estimated it's about 0.0176 for the outside conditions. Now we also have to calculate the inside conditions, and we know that's going to be 75 degrees Fahrenheit, and then we're going to follow the curved line for 50% relative humidity, and where those two lines intersect, we're going to look over at the absolute humidity there, and we can see that that one is about 0.0094. And then we can plug that information in to our latent heat equation. So we're going to use the absolute humidity in and out to get the difference in absolute humidity, or humidity ratio, times the airflow, which is 400 CFM, times our constants. So we plug that in together, and we get 15 kBTUs per hour. For the sensible heat, we have a simpler equation because we can just use temperatures. So we just plug in the 92 degrees outside minus the 75 degrees inside, and we see that that heat gain is 7 kBTUs per hour. And we just add them together. And so the answer, if you had gotten this, these numbers in your exam, the answer would be 23,226 BTUs per hour, or 23.2 kBTU per hour.